So thank you very much, Professor Kluting. See it? He taught me mathematics 40 years ago. Just a detail. So I'm honored and also slightly frightened to speak here. Ice, I think, is a fascinating substance. It starts with snow crystals. Maybe snow crystals are the nanoparticles for glaciers. But ice, to me, glaciers is also a piece of art. And I'm always impressed by the forms in which this ice appears. This is just a photo from the Vadretta Morterach in Switzerland, where I have been working for 25 years. And I also show this picture because my son is on it. He is here in the audience. It's one of the little boys there. My kids are not glaciologists, but they understand my passion. I take them along every now and then. This one you have seen before. This is a picture of when Professor Dahl Jensen, but from now on I will say Dorthe, and me were kids. In the beginning of the Qatar Summer School, you showed this picture as well. I want to show it just to thank you, Dorthe, for all this generous support you gave in the first 10 or 15 years of this summer course. It was a great adventure, and maybe we can go back there together one day and celebrate this. The Master of the Universe has done a very good job, at least for glaciologists, because he has placed the planet on a distance from the Sun that is exactly right for having alternations between glacial phases and a very warm Earth. And it's really quite critical. If you would increase the distance to the Sun with, say, 5%, the Earth would be totally glaciarized most of the time. If you will move it a few percent closer to the Sun, we will probably never have any glaciers. But we are kind of in between. So glaciers and ice sheets come and go, and that makes up our job. So that's very nice to see. This is one of my favorite pictures. It's not my picture. It's taken from an article by famous geologists. And it gives an impression of how glaciation appeared during the history of the Earth. The history of the Earth is about 4.5 billion years. And most of the time there were no glaciers, at least no traces. From the geological and geomorphological records, which I have to believe, I'm not a specialist, but I think these are very clever people. They managed to trace down to order former glaciations on the globe. And the most dramatic events were the so-called snowball Earth events, where most of the Earth was covered in snow and ice. These happened for relatively short periods and then long periods without any traces of glaciation. I've tried to give in this diagram a kind of a classification with a glacial index, which is 1, we have a snowball. When it's half, we have what we call an ice age, which the last ice age ended about 20,000 years ago. And we have the present day situation has glacial index 1/4 with ice sheets in Antarctica and on Greenland. And my interest increased more and more towards the very last millimeter of this slide, the Pleistocene, where we see ice sheets come and go, the so-called Pleistocene glacial cycles. This is a deep sea, this is an oxygen isotope record from a deep sea sediment core. I have no time to explain exactly how this works or how this graph has been constructed. I want just to summarize 2 obvious things we see here. The red curve, which shows us that climate has been cooling all the way. 50 million years ago we had a climatic optimum, and since that time it has become colder and colder. And the blue curve, the wiggling curve you see here, is a measure for the ice volume, the total ice volume on Earth. The deep sea sediments don't tell us where the ice is located, but they show the total ice volume on Earth. And you can see that the variations increase in amplitude. And the periods, the duration of a glacial cycle, so this would, at the bottom would be a glacial maximum. LGM means last glacial maximum. On the top we have the present interglacial. So it switches between these two states, and the duration of what we call a glacial cycle takes longer and longer. And this has puzzled me, and in fact I did my PhD work on this. I was at that time working at the Royal Netherlands Meteorological Institute, supposing to do research in the field of long-range weather forecasting, but I thought that's not a very promising field. So I kindly slowly slipped away to modeling ice sheets and looking at the longer time scales. And I had a director that kind of didn't mind too much. And at some point he said, you have to write a PhD thesis on this. So my PhD thesis was produced at the Weather Service, actually. And then when I did that, I left to go to the university and be in ice forever. Yes, I did a lot of computer simulation, coupling ice sheets to bedrock movement, trying to get a better description of the coupling between ice sheets and the climate, and trying to fill in some parts of the puzzle, because these glacial cycles that last about 100,000 years are peculiar. The ice builds up slowly with ice caps in northern America and Eurasia, and disappear quickly. So some people talk about the sawtooth shape of the glacial cycle. And I've tried to design computer models that could simulate this. We knew by that time that there was really a link between the varying orbital parameters of the Earth causing insolation variations at high latitudes of 5, 6, 7% that were somehow related to the evolution of these ice sheets. And I've tried to summarize in this graph, this is probably my most complicated graph, which processes are at work there. First of all, the snow line, which is the dashed yellow line here, tells me the state of the climate. Above the snow line, snow can accumulate. So as soon as you have terrain above the snow line, snow will accumulate and form an ice sheet. And when the ice sheet grows, it grows into the atmosphere. We call this the height-mass balance feedback. So it brings its surface higher and higher up in a colder climate. And that's what we call a positive feedback loop that makes the ice sheet grow and grow and grow. Then the bedrock will respond. The ice sheets become a few kilometers thick and the Earth's crust will bend. This will lower the surface of the ice sheet and slow down its growth. But the other processes, like what we call the albedo feedback, the more reflection of solar radiation, which further cools the climate. Carbon dioxide concentration may drop because of lower ocean temperatures, so there are some feedback loops that make the ice sheets grow and grow further. But there are other processes that prepare for decay already from the beginning. And one is accumulation of heat in the ice sheet. There's always coming heat from the Earth's crust, the geothermal heat flux, which normally escapes. It's not a lot, it's 50 milliwatts. But if it cannot go anywhere and you have time, it will increase the basal ice temperature. So at some time, the lower ice layers become warm, the ice becomes at the melting point, and the ice may slide over the bed. And this will make the ice sheet thinner. So that's preparing the ice sheet for decay. If at the same time the snow line is going up because there's an insolation maximum, then the decay can set in. And now we see the curious effect of the bed response. When the ice sheet thins, the bed will of course come back up, but it's delayed. And because of this delay, big lakes will form at the margin of the ice sheets, calving will occur, and the decay will be very rapid. That's in a nutshell how I see a glacial cycle. We still have problems in simulating this process, this full cycle, with coupled ice climate geophysical models. But I think these are the most important processes. So when does the next ice age come is always a question, of course. It's a peculiar question, especially since we're all talking about global warming. But there will be a time after global warming, and we can be pretty sure that an ice age will come. We need two conditions. The bed has to be up high again, and insulation has to be a minimum, so that the snow line comes down. And then the next ice age will start. And I take the courage to tell you that I think the most likely time we will have the next ice age is in about 50,000 years from now. So we have a long interglacial to do experiments with the climate system. Personally, I find this my most interesting paper. Submitted in 1985, published in 1984. It's a bit peculiar, but this is possible. About glacial erosion, because most of the time there were no glaciers on the planet, but the time they were there, they were extremely active. Glacial erosion is a very powerful mechanism to shape the landscape. And what I tried to do is, of course there were speculations about the role of glaciers in erosion, but what I tried to do is, by means of computer simulation, to see how long it would take to grow a fjord, for instance. Would it be 5 million years or 200,000 years? So I started to work on that, to construct a computer model that could do this. By today's standards, these computer models would be, students would laugh about them. They're so simple, but you have to start somewhere. And another mechanism that really seems to work is how you build a mountain range by glacial erosion. So on the picture on the right-hand side, you see a simulation where I have a simple valley in a flat landscape, and then I let it glacierize. The glacier starts to erode in the valley more than on the plateau. So the valley will become deeper. But because material is removed, the Earth's crust will come up. And this will increase the erosion in the valley, and so there's a kind of an unstable situation where mountains grow and the fjords get deeper. And this is exactly what you see in all places of the Earth where glaciers have been active. Perhaps Scandinavia is the best known example, but we see this in Patagonia, in Alaska, Western Canada, New Zealand, many places. So I always like to show this picture of the enormous range of conditions and landscape you have due to the action of glaciers. Fjords and deep valleys we see on the globe, almost all of them are due to glacial erosion. I estimate that 95% of all lakes we have on the planet are due to glacial erosion. The best examples close by are, of course, the Lago Maggiore, Como, Garda, all lakes in the Alps, in fact, Scandinavia, northern Canada, North America, all glacial lakes. If you would remove the glacial lakes, we will not have much fresh water, actually. Now I make a huge jump to a different time scale. The dripping glaciers, I call the dripping glacier story. This is the snout of the Vadretta Morteratz glacier in the Ober-Engadin in Switzerland. And I also show this picture because my daughter is on it, who's also sitting in the audience. And yeah, everybody knows that the glaciers are shrinking. This is, in a way, a sad story. In view of the long-term history of the Earth, it's nothing special. But in view of the short-term history of mankind, it is. In the course of my research, I collected many glacial length records. I took as a criterion that they should start before 1950, 240,000 glaciers, so you cannot have length records for all of them. But those records that started before 1950, which was the year I was born, by the way, there are about 500 records, and I show 20 of them here. I have no time to discuss this in detail, but at the first glance you already see that there's a fairly coherent picture over the globe. Glaciers have been shrinking since about the middle of the 19th century. We see differences in amplitude. Some glaciers like Nygaardsbreen in Norway retreated enormously, others much less. And of course it's the job of a glaciologist to find out whether these differences are due to different climatic forcing or maybe difference in geometry of the glaciers. So that's part of our job to find that out. But of course first you do raw statistics, and the raw statistics show that all glaciers are retreating. This shows the mean retreat of the glacier snout over this period from 1900 till 2010. And you can see it's only a few percent of the glaciers that have become larger. So it's the retreat in meters per year, averaged over this period. So overall glaciers have become shorter by about 10 meters per year, as an average over the globe. Well, that's statistics, but of course, as somebody with a background in physics, you want to go to describing mechanisms and processes in quantitative terms. And then you find out that little is known about the coupling between climate and glaciers. So there's only one way out, and that's go in the field with weather stations and other equipment to find out about this coupling. And you want to answer simple questions like, when in the upper atmosphere it gets 1 degree warmer, what does it mean for the glacier surface? Is it also 1 degree close to the glacier surface? Does the glacier have a microclimate? Does it melt 10 centimeters of ice per year or 1 meter? So that's when we started to organize big field campaigns. And at this point I should really acknowledge all the dedication and work of technicians and PhD students and postdocs that made this possible, in fact. But we learned a lot from that. And it also gave the opportunity to turn the statistics into something more advanced, namely design a control method with which you can take all glacier length records into account and the properties of individual glaciers to reconstruct the temperature on the globe. There are uncertainties, of course, but especially so about 20 years ago there was a big discussion and many people still didn't believe that the climate was warming. And there was a need for an independent estimate, independent of thermometers, and that could be delivered by glaciers. I have no time to discuss the technique, but this is the answer to the question, what is the most likely temperature signal on the globe that can explain the retreat of glaciers? It's the red curve here. And for the 20th century is in good agreement with the instrumental record, but in this reconstruction, the warming starts in the middle of the 19th century. This has been a big debate in the IPCC, of course. Why? Well, because it makes quite a difference for the interpretation whether the warming starts in 19th century halfway or around 1900. I'm not going to say too much about this, but it was a very welcome addition to the thermometer, so to say. Especially because glacier records come from very different part of the world where there are no meteorological records at all. Then I come to one of my babies, Glaciers Alive, together with Dr. Felix Keller. He's working at the Academia Engiadina in Switzerland. We came into this business of can we protect glaciers? We cannot stop the worldwide glacier retreat and its effect on sea level. That's impossible. There's only one way to do this, and that's to reduce global warming. But there's some special cases, like for instance mountain huts that depend on a small nearby glacier for water supply in summer, that are in trouble, and can we do something there? Or ski areas that use a small glacier for skiing purposes. So we made this foundation and started up some projects, and as Professor Kloeting already said, we will foster this also in the new project, the Balzan project, so to say. This is just an example of how you can protect a glacier. Cover a small glacier with fleece in summer to prevent the snow that has been accumulated in the previous winter to melt away. This has been done in the Valletta Fern, is a famous ski area close to St. Moritz. Maybe it doesn't look like this so much on the picture, but if this little glacier would disappear, the slope would be too steep for skiing, and they would have to rebuild the whole mountain. So they decided to protect the glacier with a fleece cover, and it works. So this small glacier you see on the picture on the left has increased its thickness by now 15 to 20 meters. And then the community of Pontresina, in which this glacier is located, became very enthusiastic, and they asked Felix Keller and me, can you not do the same for the Verdretta Morterach, which is a major touristic attraction? Well, no. On this picture you can see the little glacier that is covered by fleece at the left with the red arrow, and then you see the Verdretta Morterach. It's a huge scale difference, it's impossible. And also because the fleece cover can only be used on glaciers that are kind of stagnant. As soon as there's movement, the fleece will be destroyed, and it doesn't work. But of course we have a lot of fantasy, so we thought the best way to protect glaciers is to let it snow on them. And with traditional snow cannons doesn't work. You cannot make a watering system on a glacier or in permafrost. Snow cannons use a lot of energy which we don't want. So the idea was to develop a so-called snow cable. It is a cable with snow showers. A cable maybe 700 or 800 meters long. Yeah, and in fact, we came up with this idea, did some tests, some calculations, what it would make for a difference to the glacier, and then indeed we got the support from InnoSwiss to develop a prototype, which we did, as you can see that on the picture to the right. This is a nice system because you don't need energy if you have water at 20 bar pressure, which means that the water should come from 200 meters above. And the expansion system is so effective that it cools the droplets to -40, which means you get spontaneous freezing and you don't need any chemicals to make the snow crystals. And this is kind of ready and waiting for applications. In 1989, I published a paper on projection of sea level. I believe it's the first paper in a peer-reviewed journal about this. And with the red curve here, you can see the sea level projection as you can find in the latest IPCC report. For the specialists, this is the mean for the RCP 2.6 and 4.5 emission scenarios. Doesn't matter. You can see that there is a very small difference between what we predicted by that time and now. And it's sad to say, but in a way, one can say we lost 30 years for the energy transition. Also in that time, I gave hundreds of talks. I spoke to politicians. I was in the Bundestag. I was in the Dutch parliament. Not much happened. Now it's starting up, but so I really feel this as a bit of a disappointment in the confidence in science. But okay, this is the practice. So, glacier retreat will continue. The ice sheets of Antarctica and Greenland will lose mass, and we can be sure that sea level will continue to go up. It has gone up by about 25 centimeters over the past 150 years. Right now, it's the rate of sea level rise is about 4 millimeters per year over the past decade. So there's an increase, and I believe that the increase will become even larger. But just as an educational tool, I always like to present this graph, which perhaps, hopefully, presents an upper limit of what can happen. If you would double the runoff and the production of icebergs from the major ice sheets instantly today, you can calculate what this would mean for sea level. And it would add up to about 80 centimeters in a century. So for me, this is kind of the upper scenario. Of course, to this comes the thermal expansion, which until today takes about half of the job. So, but when we go further and further, the ice sheets will become more important and thermal expansion will relatively become less. Okay, so I have to conclude. This is my last slide. And I want to connect to this, a wish for the younger scientists. When I came to the university, it was a temple of the free thinking. When I look at the university now, it is maybe a bit harsh to say, but it's a kind of a bureaucratic advice bureau where many projects are done with lots of forms, where you have to define the output well in advance. And I feel that for the younger generation, I feel a bit sorry that you have to start in an atmosphere like this at universities. So I hope that we manage to cut down a bit on the bureaucracy in science, which is at the moment is tremendous. So that's my last statement, that I hope that for the future generation, they may slowly return to the conditions I had when I was a starting researcher. Thank you very much. I give the floor to you and to Dorthe. Oh, thank you.
Great. Thanks so much, Hans, for a very fascinating presentation. We will have a undoubtedly lively discussion after listening to the presentation of Dorthe. We have time for that. And I'm very happy that Dorthe will take the floor to basically share with us her findings about looking inside the ice sheet and telling us about her fascinating scientific journey on ice, but also to greater depths, reconstructing the past of the glaciers and telling us about what it means also for the future. So Dorthe, we are looking very much forward to your presentation. Floor is yours.
Thank you very much. And first I'd like to thank the Balsam Foundation for selecting me for this prize together with Hans. It was an unexpected honor, and I can't express how glad and happy I am about that. But I'm going to tell a little about ice core research and what it means for the climate, what we have learned from the climate research. So this is a picture we've already seen, but you can see from this picture that I'm holding a piece of ice core, and you can see there's really nice stripes in it. This is ice that is more than 20,000 years old, and we still very clearly can see the annual layers as the distance between the stripes. So I think that's what's extremely fascinating from ice cores. The very high temporal resolution we have in the ice cores, and the ability to look so far back in time, 150,000 years from the ice cores in Greenland. And together with the fact that so many things are totally frozen into the ice core, that we can see what was the temperature back in time, how much accumulation was there back in time, what volcanic eruptions can we see in the airdrops, what the past concentrations of greenhouse gases is. So it's been an extremely rich source of information of the past that nearly all climate researchers has actually used these records in their reconstructions. So I have to choose what to talk about, and to illustrate the high resolution, I'll talk a little about the ECM, which is an amazing simple measurement where you simply drag two electrodes over the ice, as you can see my colleague Anders Jensen is doing there. And just by putting a voltage between them, you measure the current, and this tells you about the acidity in the ice, which is a mean of reconstructing the past volcanic eruptions. Because when you have a big volcanic eruption, you have a high concentration, especially of sulfate, and by this you can reconstruct, we call it a global volcanic aerosol forcing, which you can see on the bottom slide here. So you can see from time to time there are some big peaks going down, and especially year 44 before Christ, we have a big volcanic eruption called the Okmok in Alaska, and we have the Tambora eruption here, 1850. So this is a record of the last 2,500 years, where we look at the past volcanic eruptions. And I'm going to tell a little more about Okmok, because that's especially interesting here, because it's the one we call the Caesar volcano. It's the volcano that kind of led to the end of the volcanic republic, because it had, after the volcanic eruption, there was quite a lot of years with cold summers. On this graph here, you can see the record from the Greenland ice core, from where you can see year 44 BC. There's a strong amount of sulfate in the ice core, showing there was a big volcanic eruption. This is put together with the tree ring record, and you can see following this 44 year, there are about 10 summers where the tree rings are very thin. And this illustrates that it's been cold and dark summers. And we know from reconstructions in a very more recent paper by Joe McConnell, where he's modeled it, that the temperatures were probably 2 degrees colder annually and 4 degrees colder in the summer. And there was a drought there. There was very low precipitation, so there was famine because there was no food in that time. The paper was published together with my husband, J.P. Stephenson, who's also with me today, and also ice core climate scientist. So I see this is an example of how the very high resolution ice cores can be combined with other records to tell about what has happened in the past and understand what can volcanic eruptions do with our climate system. So just to try to kind of classify volcanic eruptions, we have the Volcanic Explosive Index, and the Okmok volcanic eruption was a scale 6. It is classified by the amount of erupted tephra into the atmosphere, and we can see how much damage and how many hundred thousands of people died because of this event. One of the bigger events we can see, I don't know what's happened there with the pink, but is one of the bigger volcanic eruptions we can see is Tambora, which was further back in time, and was a bigger volcanic eruption in Indonesia. And in the ice cores, we see Toba 74,000 years ago as one of the biggest eruptions we see. And when you look at the ice cores and look at the frequency of these big eruptions, we can see they happen about every 50,000 years. We still have so few of them that it's difficult to exactly decide. It's all statistics, something you know very well in Italy, that it's difficult to predict when the next volcanic eruption would be. But this ends my case 1, that volcanic eruptions are seen to be able to darken and cool the atmosphere, most of them only for some years, but the bigger ones like Toba can be really serious for our climate system. So when will the next one happen is important. So I'll go to my second case and go and look at the long climate records we have from the Greenland ice cores. Here you can see a record starting 140,000 years ago and going to the present at 0, and it's the stable water isotopes where we measure a proxy for the past temperature on the Greenland ice sheet. You can see on the climate record that the last 11,700 years is our present interglacial period, a very warm and stable period. But if we go further back in time, we go into the glacial period where you see that it's colder but much more unstable, and we see big climate changes with increases of temperature of 15 degrees over less than 100 years. So the climate can be more unstable just internally than we see now. But if you go back to the last interglacial, from 115 to 130,000 years ago, we see the previous Eemian period, where we over Greenland can see that the temperature was 5 degrees warmer than the present. So this is a very, very interesting climate period, because that's what we are facing now, a warming climate. So the obvious question is, how much of the Greenland ice sheet melted away during this period? And we see that being 5 degrees warmer for about 8,000 years, Greenland, the elevation or the thickness of the Greenland ice sheet decreased with 400 meters of the 2,600 meters we have. And we actually see that we have ice from the Eemian ice core, from the Eemian period, in all our ice cores from North Greenland to South Greenland. So our conclusion is that Greenland at most lost 25% of its mass, causing a sea level rise of 2 meters. We know the global sea level rise at this time was 5 to 9 meters. So we know there must have been a very big contribution from Antarctica as well. But the interesting thing is that if you look at the new IPCC report that came out last year, in nearly all the predictions, the temperature over Greenland with the Arctic amplification will be 5 degrees warmer before year 2100. So we are facing the same warm conditions that we had during the Amian. So we are starting the process of reducing the ice masses and increasing the sea level rise. Luckily, it takes a long time to melt ice, so it's not something that happens tomorrow. But the big question is, do we want to face this and do we want to continue this game? So I'll turn to my third case, because when we drill right down to the bottom of the Greenland ice sheet, we recover sediments from the bottom of the Greenland ice sheet. It's sediments that's been entrained into the ice, but also direct sediments under the ice. And we've been looking a little into these sediments, and it's super fascinating because when we look at them, we find directly small twigs and pieces of moss and pollen in the ice sheets. They've been preserved there because it's been cold and frozen all the time. So they look totally pristine, but when we try to date the ice and the rocks around them by radiogenic methods, our first estimate is that this ice is probably 1 million years old. So these macrofossils we find in the ice have actually been encapsulated in the ice for 1 million years. So the present Greenland ice sheet is probably 1 million years old. But when we look at this material, we see that it's all remains of a boreal forest. So this is forest we see in North Canada, we see it in South Greenland, and we see it in North Sweden as well. And we know that the coldest month cannot be colder than -17, and the warmest months have to be +10 degrees for such a boreal forest to stand. So if we compare it with the temperatures we have over Greenland now, remembering to uplift the bedrock, as Hans has told you about, our conclusion is that it has to be 10 degrees warmer over Greenland to sustain this environment. So that's the conclusion of the third case, that the Greenland ice sheet has survived many glacial and interglacial cycles, but around 1 million years ago it's been gone, and there's probably been a warming of 5-10 degrees at this time. So if we warm the climate with 10 degrees, we're going into a situation where we can actually melt the full Greenland ice sheet away. So again, we can say, is that something we want to do? We have all the ice cores in Greenland, in our freezer in Copenhagen, and it's our program right now to make more investigations of this basal material, because the radiogenic methods are getting so good that we're able to make much better dating with the quite sparse material we have from these 10 centimeter thick ice cores going to the bottom of the Greenland ice sheet. Now I'll turn to the last case here, because if you look at the Greenland ice sheet, you can see that we know that there's a snowfall every year of about 650 gigatons, but we also know it's melting about 820 gigatons. So Greenland is losing these 270 gigatons of mass each year, which is about 0.7 millimeters per year of the sea level rise of 3.5 millimeters per year. But half the mass loss is from melt along the margin under the snow line, as Hans told about, but the other half is actually ice that's streaming out in ice streams from the center of the ice sheet in like an ice flood, cutting its way out through the ice sheet and melting and carving icebergs out into the ocean around Greenland. We don't understand these ice streams very well, so at present we're drilling an ice core through this ice stream. We call it E-scrip, and we came home from the project this summer. We just have 250 meters to drill before we reach the bedrock, and we want to learn how the water is flowing under the ice stream, how the ice stream is sliding, and how it's cutting itself through the big ice sheet. Because I think this is the biggest uncertainty for knowing what the sea level rise will be into the future, that we don't really know what happens with these ice streams when the climate warms. We know if it warms, we'll melt more along the margin, but the ice streams seem to be accelerating, especially because the ocean is warming, but we also see some ice streams are reducing their velocity. And if we have to bring the uncertainty on the future sea level rise down, we have to look at the ice streams, we have to understand the ice streams. But this also leads me to my very last slide, because what happens when all this fresh water goes out into the ocean? This is something I've started to studying here in the more recent years, where I've also got a position at the University of Manitoba in Canada, and we're starting to work a lot with the communities around the Baffin Bay between Canada and Greenland, because when we get all this fresh water out, both from the melting ice, but also from the increasing precipitation in the Arctic Ocean, we change the ocean circulation, and we also change the conditions for the living resources in the area, the marine mammals, that are very, very important for the northern communities. So I would like to make programs to understand more what happens when the ice melts and what it means for the people living in the north. So this is the very last case. How will these changes change the conditions for the people living in the north? And it is really urgent to reduce emissions of greenhouse gases, so we start to reduce the big changes we already have programmed into the climate system. That would be my message. So I'd like to stop with this slide, and on behalf of both Hans and me, we again would like to thank the Balsam Foundation for this amazing recognition, but we'd also like to thank all the researchers that has been involved in these big programs that we both have done, and especially the biggest thanks to all our young and brilliant students. Without them, nothing of this could happen. So thank you very much.